Good morning. My lecture is on EC370 digital image processing. The today's topic is image segmentation. So in this lecture or in this topic, we deal with what is image segmentation, what are its applications, and what are the methodology we used to perform the segmentation. The reference textbook we follow are Digital Image Processing by Jayaraman and Digital Image Processing by Gonzalez. So in this lecture, I will be focusing on one of the methodology which is used for image segmentation. So first of all, what is image segmentation? As it is mentioned, shown here, image segmentation is the process of partitioning the digital image into multiple regions. So there are various applications associated with. So I will show you an example. Here you can see two images, one grayscale image and a color image. The grayscale image is the original image and the second color image is nothing but the segmented image. So don't feel that segmented image will have color components. It's not like that. So in the grayscale image, it is of vegetables. Segmentation is the process of partitioning or finding out the boundary of each objects in the scene. Here the different vegetables, whose boundaries are being located and different colors are being given to the segmented outputs. So here in this example, grayscale of the particular image is considered for performing this task. Similarly, many other features considered for performing the task. So to represent the image segmentation in terms of an equation. So here the entire image is considered as a region R, and the sub-regions or the segmented regions are named as R1, R2 up to Rn. So the properties are the union of Ri is going to be equal to the R. That is, you have different regions. If you consider all the regions, it put together form the original image. And if you consider individual regions Ri, they are going to be connected components. And there is no overlap between two different regions. And there is also a logical predicate assigned for each region. For example, one region, let us say the average intensity is specified to say 100. So in such a case, that particular region will have a logical predicate of average gray level is 100. Same way, other features can be assigned. For each region, there will be different logical predicate assigned. Now, it is put in once more, that is the purpose of image segmentation is to partition an image into meaningful regions with respect to particular applications. And the features used, some of the features used for performing this task are gray level, color, texture, depth, motion, etc. So why we need image segmentation? So there are many applications, few applications are listed over here. One is image understanding. And the second one mentioned here is the object-based measurement. There are many cases, remotely we want to measure the object, maybe its size, shape and other aspects. Segmentation is the first task to be carried out. So another important application is video compression. In MBUG 4, the image is segmented into different objects, then each object is encoded. So it is very much used for in MBUG video compression. It is also used for path planning of mobile robots. This is a part of an image and understanding task. Here image processing or image segmentation is a basic of initial task to be carried out to understand the scene. And these are the different techniques which are available to perform the segmentation. So one is thresholding based approach, second is region based approach, clustering based approach and edge based approach. So in this lecture we look into the thresholding based approach. Okay, look at the pictures over here. There are two pictures you can see. It is the histogram of images. In histogram, your x-axis is the grayscale, number of gray levels available in the image, and the y-axis is the number of occurrence of the image, the gray level values. In the first image, it is clear that there are two clusters. You can see the gray levels are forming two clusters, and there is a valley point between the two clusters. Here we understand that the clusters, one is the foreground and the other is the background. So if you perform the thresholding between this foreground and background, so you will be able to segment out the region easily. And if you look at the second histogram, there you can see three clusters shown over there, and it give you two threshold points. Now what it indicates, there can be one background and maybe two foregrounds present over there. So in this case, using two different thresholds, you will be able to segment two different objects from a background. So if you look at the description, it is mentioned global thresholding. Global thresholding means the entire image is applied with a threshold. So it is not limited to a portion of the image, it is applicable to the entire image. The first case, you need to have only one threshold, but for the second case, we have two thresholds. So when we have more number of thresholds than one, we call it as a multiple thresholding based approach. And the last one is called variable thresholding. In certain cases, there will not be these value points available between the objects present in the image. In such a situation, what you do is, you divide the image into different regions, then the thresholding will be carried for each region separately, then the sub-regions will be joined to form the final image. The example will be there in the coming slides. So now look at the image. Here my intention is to make you understand the impact of noise over the image and its impact in the resultant thresholded output. So you can see 6 images over here, and the first one is an original image, or maybe the first, and the fourth one is its histogram. So it's a clear image, there is no noise, so the histogram is very narrow. In the second image, some amount of noise is included into it. So that is the reason if you look at a histogram just below, the width of the histogram cluster is becoming wide, but the value point remains there. But if you look at the third case, the noise level is much high. Now if you look at the histogram, there is no value point at all. So such a situation, it is very difficult to find the threshold values that may give you the best possible segmentation. In the third situation, it is not possible always to get a best case. Maybe there can be some issues in the resultant case. So in such situations, we may go for variable thresholding or some other approaches for getting the best results. This is another impact of illumination on the image. You can see that with the illumination here, image 1 and image 2, they are two different scenes, and they combine. The 1 and 2 is combined to form the third image. When it comes to the third image, you can see that there are two value points present in the histogram. But if you look at the image, it is clear that you have one background and one foreground present over there. So now there is a confusion which threshold need to be chosen. So in such situations, either you have to go for variable thresholding, or sometimes you may have to consider something like optimal thresholding. Anyway, there are different algorithms available for performing or finding out the threshold in such situations. You will start with some basic algorithms, then we will move on to the optimal algorithm and so on. So now just to summarize, so you have an image with noise free and if it's noise free, the thresholded output or segmented output is clear. If it is low noise, still your output is okay, but some noise can be seen in the resultant output. And if the image is with more noise, then the image quality is much poor. So if you consider the histogram of these three cases, it looks like this, where the case 1 noise free and low noise, you will have clear value points in the histogram, but high noise case you will not get any value point for choosing the best threshold. So in such situation, we need to go for different algorithms. Okay, we will start with a simple automatic thresholding algorithm. This is the very simple approach where you will find a threshold for any thresholding based segmentation. Here, based on the image or the mean value of the image, you will try to choose a threshold, and based on the threshold, initially you divide the image into two regions. One is foreground and the other one is background. Once it is formed, you will try to find out the mean of these two regions. In step 2, you find out the regions, and step 3, you find out the mean of these two regions. In step 4, you will take the mean of these two means, and that will be your new threshold. So now steps 2 to 4 will be repeated until the t value become almost constant or the variation is within a specific threshold level. So this is a simple approach. Maybe it may give a local minima, or we can say that it give you a result, but it may not be the best possible with the thresholding system. So in such a case, you may think about optimal thresholding. In optimal thresholding, you will try to find out the best possible threshold based on some approaches, mathematical approach and optimization approach. Here, you will try to maximize a particular criterion function. So you will define a criterion function and you will try to maximize the criterion function to obtain the best threshold. And Otsou's method is the best threshold which is available for us to study. So here the Otsou's thresholding approach is an optimal method is summarized in this particular slide. Before going to this, please recall the histogram equalization which we have done for image enhancement. In histogram equalization, we had a table, and in that table the first line was the number of the elements in the image, second row was the histogram, third row was cumulative histogram, fourth one was normalized cumulative histogram. Here also the tabulation and the process is almost in line with the histogram equalization. If you look at the first point to be calculated is the normalized histogram. From the normalized histogram, you will calculate cumulative sum in step 2. Now if the formula is given, P1 of k is summation of I equal to 0 to k pi, where pi is nothing but the normalized histogram of that particular k value. So in this case, pi of P1 of k is a cumulative sum. And if you look at the third one, it says it is cumulative mean. And if you look, that is represented with m of k. And in cumulative mean, only one change you can observe, your cumulative sum in each instance you multiply with the gray level value also. And now go to the fourth step. It is called global intensity mean. It is named as mg. In the previous case, cumulative mean was mk, and this is named as mg. And if you try to tabulate mk, and the last calculation which you get will be the mg value, because when for k value, when you give a value of 255 or L minus 1, then you will get the mg. The difference between mk and mg is for the last instance, or mk with k value, L minus 1 gives you the mg value. And the fifth one is called the criterion function in this optimal thresholding. The criterion function is the variance. It is sigma square b of k. It is computed based on all the factors which are already computed in step 2, 3 and 4. Here again, you need to tabulate the value of sigma square k for all the value of k. K will be ranging from 0 to 255. It need not be to 255 always, because our aim is to find out the threshold. Most of the time the threshold will be maybe in the halfway. So in such case, if you want to reduce the computation m of k, the k value can be limited to maybe some range based on our intuition. Anyway, if you tabulate it fully up to 255, it will be clear, or if you look at the value of sigma square k, it can be seen that at some points there will be a peak value for sigma square. So now for a particular value of k with sigma square value is the maximum, that k value is considered as the optimal threshold. In previous other cases, we were not optimizing any criterion function. Here, we are maximizing this criterion function that is called between class variance. The between class variance is maximized, and the k value corresponding to the maximum value of variance is taken as the optimal threshold. With the step 6, we will be able to get the optimum threshold value. Based on this threshold, you can generate or maybe you can perform your segmentation. And in step 7, it is a measure of separability. It is defined by Otsu. And now look at some example. Here you can see that in first row, you have an original image, and you can see its histogram. The histogram doesn't have any value points. Still, with the Otsu's method, the third image is the result of the Otsu's space segmentation. Somehow the segmented image is acceptable. But if you perform a pre-processing to the image, see at the second row, first image, a smoothing operation is carried out to the original image, original noisy image. Now if you look at the histogram, you see that there is a value point visible there. So now if you apply the Otsu's method, the segmentation will be much better. So here, with Otsu's method, after smoothing with 5x5 mask, the quality of the image is much better. Now to summarize the activities done with thresholding based segmentation. In the thresholding based segmentation, we have three methods, and one is called global thresholding. In global thresholding, you have single threshold and multiple threshold. And the second case was variable threshold. In single threshold itself, you discuss iterative algorithm and optimal algorithm. The thresholding which we left out, or the remaining, is called the variable threshold. In the next slide, we discuss about the variable threshold. So if you look at this image, it is the first one is the original image. Second one is its histogram, and third one is a result based on iterative algorithms, and the fourth one is based on Otsu's approach. Now here we are trying to show how the variable thresholding is applied. In the fifth one is what they have applied is they divide the image into 6 regions. It is evident in the fifth image, and on each region the Otsu's threshold is applied. Now, after applying Otsu's threshold in all the different regions, you can see that the sixth image is the segmented image is much better than the results you obtain with Otsu's method as well as iterative method, which is given in images 3 and 4. So, based on the applications, you need to choose between variable thresholding, optimal thresholding, or iterative approaches. So, to understand more about these topics, you can refer the references Jayaraman and Gonzalez. So and the remaining part, there are 3 more sessions, that is your segmentation can be done based on region approach, clustering approach, and your edge-based approaches. These things will be discussed in the coming lectures. Thank you.